So we're entering chapter 6.3, which is exponential functions. And in this section, we'll be covering a couple of different things. We'll be covering, first of all, how to evaluate exponential functions. We'll be looking at the graph of the exponential function. We're looking at the definition of the number e, put it a little separately, and then we're going to look at solving exponential equations. So the very first thing is how to evaluate an exponential function. If I wanted to, say, find 3, and this is done with the calculator, to evaluate say powers of 3. And if we wanted to find, say, 3 to the power 1.7, sorry, 1.7, we would go to the calculator, press 3, the unscap button, and 1.7, and enter. And then we will take whatever number of decimal places we're required to take. So this is equal to 6 approximation, because the decimal doesn't really have an end. 6.473000784. Or if we wanted to find, say, 3 to the power 1.732, 3 to the power 1.732, and then press enter and get whatever number of decimal places we want to get. We're going to approximate this as 6.704 617606. The next thing I want to speak about is, before going anywhere with this, is the laws of exponents. Laws of exponents. And these are simply a reminder of some of the rules that we've used with exponents in the past. If we have, say, a to the power u times a to the power v, this is equal to au plus v. A to the power u v, this is simply the product of u times v as the power. If we have a to the power b all to the power u, then this is a to the power u times a times b to the power u. 1 to any power is 1. What else can we remember here? A to the power negative u is 1 over a to the power positive u. And a to the power 0 is equal to 1. A over b to the power negative u is b over a to the power positive u. So this is just a quick refresher of those rules that we uh, use when we're working with exponents. Remember that u, v, a, and b are real numbers, and that a is always a number that's greater than 0. We can probably write that, okay? U, v, a, and b are real numbers, and a is greater than 0. B is also a number that's greater than 0. Before this, any of these rules could work. That's just some of the ground rules related to exponents. And next, we want to define exponential growth. The exponential function form is f of x is equal to ca to the power x. A is a number that's positive always, and a cannot equal to 1. C is not equal to 0 and is a real number. The domain of the function f is all real numbers. The base a is called the growth factor, and c is referred to as the initial value. So we want to go ahead and see if we can figure out how when is a function an exponential function. Okay, so just a quick reminder that for a function to be linear, functions have the same slopes. For example, if I have, say, a table made up of x and f of x, and I used a few values here, such as -1, 0, 1, 2, and 3, and 2, 4, 6, 8, and 10, and I attempted to I think instead of have the same slopes, we can say have an average rate of change, or average rate of change. I'm struggling with the definition. How linear functions have a constant average rate of change, which is just another way of saying a constant slope. Now, if we consider the values here and we figured out the slope, okay, slope is y2 minus y1 over x2 minus x1, which is equal to positive 2. Then if we look at the second consecutive pair of values, and we have 6 minus 4 over 1 minus 0, we would have 2. And between 8 and 6, we have 8 minus 6, y2 minus y1 over x2 minus x1 would also give us 2. And finally, between 10 and 8, y2 minus y1 over x2 minus x1 gives us that constant slope. So the average rate of change slope for every 1 unit increase in this case is equal to 2. The y-intercept occurs when x is equal to 0, and from that we can see that the y-intercept is equal to 4. So the equation is y is equal to 2x plus 4, from the format y is equal to mx plus b. So the equation that would have generated these set of values in the table would be y is equal to 2x plus 4. Now, if we wanted to kick this a step further and look at what would constitute an exponential function, if I have fx and f of x, and let's just use the same set of values here from -1 to 0 to 1, 2, and 3. And I can start here with 3 over 2, 3, 6, 12, and 24. And if I try to get slopes here, I'll be having 3 minus 3 over 2 divided by 1, which is 1.5 minus 3, or 3 over 2. Then if I went to the next pair of values, I would have 6 minus 3 over 1, which would give me 3, and 12 over 6, 12 minus 6 over 1, which would give me 6, and so on. We can immediately observe that this is not linear, because the slopes are not the same. The average rates of change are not the same. So we can again try to observe this and see what's happening. What about if we take, say, consecutive ratios? Okay, for each unit increase. Remember, we're increasing from -1 to 0, from 0 to 1, from 1 to 2, and from 2 to 3, and so on. And if we took consecutive ratios, say 3 divided by 3 over 2, this is equal to 2. Or 6 divided by 3 is equal to 2. Or 12 divided by 6 is equal to 2. Or 24 divided by 12 is equal to 2. So taking consecutive ratios instead of average rate of change instead of slope gives us the same constant ratio. And that identifies this, since the consecutive ratios are constant, this is an exponential function. So this is an example, a good example of an exponential function. And this one is a good example of a linear function up here. So the growth factor, remember earlier we spoke about the equation of the exponential, the exponential form of the exponential function. F of x is equal to c a to the power x. In our example here, the a, the growth factor, is that constant ratio of 2. And the initial quantity, the initial amount, is equal to 3. That is occurring when the x value is 0. So the exponential function for this case, particular example, is 3 times 2 to the power x. And then we can look at a final case where something is neither linear nor exponential. And I'm going to use the same set of x values here, -1, 0, 1, 2, and 3. And for f of x, I've got perhaps 6, 1, 0, 3, and 10. If we try to figure out slope here, this would be 1 minus 6 over 1, which is -6. 0 minus 1 over 1, which is -1. 3 minus 0 over 1, which is 3. So clearly not linear. Okay, since the average, the rate of change, the slopes are not the same. Now, if we could take consecutive ratios, A is 1 over 6, and A is 0 over 1. A is 3 over 0. A is 10 over 3. Again, the consecutive ratios are not constant, so not exponential. So this function represented by the table here, by these x values, do not demonstrate either a linear function or an exponential function. Now I want to speak about the graph of the exponential function. And if we were plotting the graph of, say, f of x is equal to a to the power x for a greater than 1, there's some characteristics of this graph that remain the same. So this is y, this is x. And an exponential graph typically looks like this. And the intercept, the y-intercept of this graph is at the point 0 and 1. The value at -1 is 1 over a. And the value at +1 is a. So the domain, just some quick attributes, the domain is all real numbers. The graph goes from negative to positive infinity, negative infinity on the left and positive infinity on the right. The range, the graph, the lowest, the graph does not go below the y-axis, so it's from 0 to infinity. It just continues to climb. No x-intercepts. In this case, the x-axis is the horizontal asymptote. F of x is increasing over negative infinity to infinity over the entire domain. Graph contains the points -1 and 1 over a, 0 and 1, and 1 and a. So I want to go ahead and show you what the typical graph of, say, f of x is equal to 3x looks like. And I'm going to use a slide from the textbook PowerPoint to demonstrate this, because and then we're going to also graph it with our calculator in a minute. But this is what the graph of f of x to the power 3 looks like. Things to point out: notice that 0 and 1 is here, 1 and a, which is 3, is here, and -1 and 1 over a are located here. Okay, and you can see the attributes of this graph as similar to the general form. If you wanted to graph this with your calculator, you would just go to your calculator, y 3 to the power x, and perhaps adjust the window just a little bit to say -5, +5. We don't want to see very many values below the y-axis, so maybe -1, and maybe leave it like that and see. And you can see the graph of y equal to 3x, 3 to the power x, with your calculator. Now, I want to explain a little bit about transformations as reflected, transformations as understood about a graph. Let's first look at this example again provided by our Pearson slides here. No, this is not the one. I wanted to look at slide 28, this one. So I'm going to copy and paste this slide here. And this is discussing the graph of 3 to the power -x plus 1. So remember that -x represents a reflection about the y-axis. In other words, all of the x values change sign. All of the x values have their sign changed. That's the first transformation, is to do the reflection. And then our second transformation, +1, is moving the graph up one place. So I'm going to try to put that on the side here. There we go. So in this case, we're moving our graph up one place. Trying to expand this a little. Okay. And that shift is up 1. Notice how that impacts the domain of the graph. Not the domain. The domain is still going to remain unchanged, negative to positive infinity. But the range is no longer from 0 to infinity, because we've lifted the graph up, and that y is equal to 1 is now a horizontal asymptote. The y-intercept, instead of being, has moved up from 0, 1 to 0, 2, because we've lifted the graph up one place. So be careful with your transformation shifts. Again, you can do this as a series of shifts with the calculator. I can show you what I mean by that. So I know I have the graph y is equal to 3 to the power x. Now I'm going to do the first shift by 3 to the power negative x. And I see that that reflects the graph on the y-axis. And then if I added 1 to the function, the graph now is moved up 1 unit. All of the y values are moved up 1 units. So please take a little time to observe how that transformation left or right, the reflection on the x-axis, on the y-axis would change the the signs on the x values. Let's just make a quick note here. Reflection, y-axis, signs, change for x values, and shifting up or down, sign, keep writing sing here, sign, change, y values. And then think about how this impacts the domain and the range in general. Next, I wanted to speak about the number E. So the number E is that base E is widely used in industry in calculating everything from bacteria growth to decay of radioactive substances. It's also extensively used in population growth and in the finance industry. That number um, is actually a mathematical definition, which is probably does not have any meaning at this stage, but 1 to the power n is n. The nice thing about it is that we don't have to worry about what this really mean in terms of the definition. This is the calculus definition. What we're concerned with is what the number is actually is. If you go to your calculator and you wanted to see what E actually is, you would simply press second, the ln natural log button, and you would see E. And let's take E to the power 1, which is E. And that's the number that E is approximated 2.7188281828, continuing recurring 1828. So E is approximately 2.72. The wonderful thing about E is that you can actually graph it, and with your calculator, E to the power x, and get your classic exponential graph. hold on a second. Let me do this to identify the graph. And then I want to go ahead and capture this and put it into our notes. Okay. So right here, and mind you, the attributes still remain the same. Uh, we would have at 0, we would have 1, as you can see from the graph here. At -1, we would have e to the power -1, or 1 over e. And at +1, we would have e to the power 1. So I guess by now you're probably asking yourself, why is all of this important? Well, the only thing I wanted to show you is that you can actually reflect this graph, and I wanted to just show you the process of reflecting it over the doing a reflection here. Let's look at a simple reflection of this graph. Okay, so I've got, so this is slide 32, and oops, that didn't come out right. Let's go ahead, go back to this PowerPoint. I'm supposed to have copied it. Copy. And then I want to paste it in here. All right, that's perfect. So, oops, still not what I wanted. One last time, we're going to try to do this. If not, I'll just not do it, okay? Um, you know what? This was the function I wanted. I don't know why I'm not seeing it. Okay. Okay, here we go. This is exactly what I wanted. This is the changing the graph of f of x is equal to negative ex plus 2. So in this case, the graph is reflected on the x-axis because the negative sign is in front of the function, and the plus 2 on the x means that it's reflected 2 units to the left. So um, reflect x-axis, shift to left. And you can see some attributes that the domain is still negative to positive infinity, but the range is still negative infinity. I'm sorry, the range is now, because the graph is below the x-axis, only from negative infinity to 0. Notice how the intercepts change for this, because the graph is shifted 2 places to the left. We're subtracting 2 places from of the um, each of the x values. So reflecting on the x-axis means changing signs on y values, then subtracting 2 from the x values to do our transformation, okay? To get our transformation done. All right, our last objective now is to solve equations, solving exponential equations. And this uses the theorem that if a is equal to a to the power u is equal to a to the power v, then u is equal to v. Now, this is a fairly reasonably straightforward application. So I'm going to give you a few examples here. Say e to the power, sorry, let's start with something simple. For if 2 to the power x is equal to 2 to the power 4, then x is equal to 4. If 2 to the power x plus 2 equals to 8, we have to go about and make the basis the same. So 2 to the power x plus 2 is equal to 2 to the power 3. This implies that x plus 2 is equal to 3. So x is equal to 1. If we've got, say, 9 to the power 2x minus 5 is equal to 27 to the power x. 9 and 27 are multiples of 3, so this is 3 squared to the power 2x minus 5. And this is 3 cubed to the power x, which we know we just multiply the exponents here. So this is 6x minus 10 is equal to 3x. Sorry, 4x minus 10 is equal to 3x. So x is equal to 10. Okay, so that solution set is simply equal to 10. I've got, say, 4 to the power negative x is equal to 256. So 4 to the power negative x is equal to 4 to the power 4. So negative x is equal to 4, so x is equal to negative 4. So solution then, negative 4. Doing a lot of fast examples here. 3 to the power 4x plus 1 is equal to 9. So 3 to the power 4x plus 1 is equal to 3 squared. So 4x plus 1 is equal to 2. So x is equal to 1 over 4. Let's look at a few examples using the base e. E to the power x is equal to e to the power 5x plus 36. So x is equal to 5x plus 36. So 4x is equal to negative 36. So x is equal to negative 9. e to the power x squared is equal to e to the power 15x over 1 e to the power 50. So you want to say this is e to the power x squared is equal to e to the power 15x. Then use properties exponents to make this a negative power. E to the power x squared. Now we combine we add the two, this is multiply. We add the two powers, so this is 15x minus 50. And now we can equate the powers, so x squared is equal to 15x minus 50. So x squared minus 15x plus 50 equals to 0. Factoring, we've got x minus 10, x minus 5 equals to 0. So x is equal to 10 and 5. One final example. E to the power negative x squared is equal to e to the power 5x times 1 over e to the power 6. Very similar problem to the previous one. E to the power negative x squared is equal to e to the power 5x times e to the power negative 6. So e to the power negative x squared is equal to e to the power 5x minus 6. So at this point, we can go ahead and equate the powers. Negative x squared is equal to 5x minus 6. Adding x squared to both sides, we get x squared plus 5x minus 6 is equal to 0. And factoring, x plus 6, x minus 1. So the solution set is negative 6 and positive 1.